Okay, and this is the corresponding mask layout of a one transistor memory cell, and the same one transistor memory cell we can able to create a pseudo generators, that is a pseudo random code generators we are going to see. So as in the previous class, in the computer communication network, sir was discussing about checksum values we need to generate it. So we are going to use the checksum values in order to generate the flow control and error control mechanisms for error detection and error correction methodologies in the digital data transmission. So if you want to create those checksum values, then we need to use a pseudo random generator signals, we need to use it. So in order to generate those pseudo random generators, so we have used a pseudo static memory cell. So with the use of this NMOS pseudo static memory cell, we can able to generate a random numbers, and these random numbers will be obeyed depending upon some certain geographical structure. Okay, so based upon this geographical structure, we can make use of these checksum values, and these checksum values can be obtained for the data what we are going to transmit from the source to destination type, destination side, depending upon the checksum what we are going to attach at the center side. So at the receiver we can able to see that okay whether the data has been affected by error or not by looking at the checksum values only. So for each messages we will be attaching a different checksum values. So depending upon the checksum value what we will be having at the receiver side or a destination side. So based upon that we can see that whether the successful data transmission has been taken place or not through the use of this checksum values. So you can see here for that we have a pseudo static memory cell over here. So we have a two clocking signals, so that is a phi 2 bar we have used, phi 2 signal we have used, means we have indicated two frequency values, and the output you can see here there is a two inverters terminals we have created, and the pull up and pull down transistors, that is the ratios. For the first transistor it is 8:1, and for the second transistors we have given it as a 4:1, whereas for the read pin and the write pin the pull up and pull down transistors are equally, means equal impedance aspect ratios has been created for the substrate and the drain terminal. So therefore the pull up and pull down aspect ratio for them it is 1:1, and for the 1:1 for the read operation also. Okay, so this is the circuit diagram for the static memory cell along with the stick diagram. The next one is the same thing we are going to implement through the use of CMOS technology. So when you want to use the same implementation, that is the pseudo static memory cell, we need to use both complementary metal oxide semiconductors. That is nothing but we need to use a PMOS transistor also and NMOS transistors also. So therefore we have replaced the NMOS transistor with the transmission gate. So why we have replaced this NMOS transistor with the transmission gate is generally transmission gates will provide a stability for the data transmission from source to destination. So therefore we have replaced the NMOS transistor with this transmission gate terminal. So with the use of this transmission gate terminal we can able to create this that is a pseudo codes for the static memory cells. Okay, so this is the circuit diagram which you are going to use for the static memory cell implementation, and the corresponding stick diagram has been written over here. Okay, so you can see here we have a VDD and VSS, it has been cross connected. It indicates that it is a CMOS technology what we have used, and there is a demarcation line in order to differentiate between the pull up network and a pull up network. So this is the Mos layout for both for the NMOS pseudo static memory cell. So you can see here we have used the via contact cuts wherever there is a combination for the source to drain, that is from the pull up transistor to the pull down transistors. So as we have used the two buses for the bus architecture for the A and for the bus B, and along with that we have used the clocking signal, that is phi 2 clocking signal we have used, and we have used the read pin and write pin for the A and B terminal, that is for the bus A and bus B for the read operation, and for the write operations we are using only one signaling line. Okay. So this is the NMOS pseudostatic memory cell which is using two buses. Okay. So the next one is implementation of the dynamic memory cell by using 4 transistors. So in the previous cases we have studied the dynamic memory cell implementation by using the 3 transistors and a single transistors. So now we are going to do the same implementation for the use of 4 transistors. So you can able to see it has been divided into 3 blocks. So that is nothing but block A, block B and block C. So you can see here there are these are the different versions how we can able to implement. So that is what it has been highlighted in this diagram. So in the first diagram you can see here since if you remember we are going to use this dynamic memory cell in 2 mode, that is one we call it as a pre-charge mode and one more we call it as a conduction mode. So if you want to make your pre-charge mode and conduction mode means then we are going to use the 2 clock signals, and these 2 clock signals will be complementary to each other. So we have used the phi 1 clock signal and also we have used the phi 2 clock signal. When one transistor is in pre-charge mode means and one more will be in the conduction mode, and if the same transistor is in conduction mode means then the other transistor will be in a pre-charge mode. So that is how we are going to implement this dynamic memory cell by using a 4 transistor. So you can see here the gate capacitance C1 and C2 which has been connected to the bit N and bit N1 bar, whereas the transistor T1, T2, T3 which has been connected over these bit terminals, whereas we are going to connect the VDD's values by using a 2 PMOS transistors, that is nothing but from the T5 and T6. So since these are giving the excitation values or the excitation levels along with the bits representation, so therefore it has been connected to the pre-charge mode, and this pre-charge mode in turn which is connected to the row coincidence which are connected to either T3 and T4 and which in turn connected to your T5 and T6. So that is how one we can do the implementation by using a 4 transistor dynamic memory cell. And the second one is, so we can the inner part whatever we had, since you can see the drain and the drain of one terminal which is connected to gate of another terminal, that is T1 and T2, and the source of one terminal it has been connected to the gate of another terminal. So we can make use of this combination through the use of the inverters. So therefore the T1 and T2 we have replaced with the 2 inverters, so which will act like a capacitance will be created, that is a parasitic capacitance will be created in the second case. And you can see the third case, so where we have using the symmetrical representation of the dynamic memory cells. So with the use of 2 input-output buses we can able to implement. Okay, so these are the different combinations how we can able to create the dynamic memory cell by using a 4 transistors. So you can see at the 3 different cases, for the case A, case B and case C, we can able to use or we can able to implement a dynamic memory cell. Dynamic memory cell. So the next one is the JK flip-flops. So still now we have done with only the main analysis of your circuit design concepts, or it may be timing constraints, which is related to most of the cases it is related to the combination circuits only. Now it is necessary for us to go in detail about the sequential circuits. So the first sequential circuit what we are going to use, we call it as a JK flip-flops. So generally this JK flip-flop, what are the terminals it will be having is, so it will be having a 2 input signals, mainly that is a G and K. In order to stabilize the JK flip-flop, so we are going to use a clock. So the clock what we are going to use or what we are going to represent it in this diagram, it is a negative clock triggering pulse. So whenever the clock goes from high to low, the corresponding change in the input, you will be getting the corresponding changes in the output sections, that is nothing but Q and Q bar. So there are output sections what we will be having is 2 values, that is Q and Q bar, and in order to reset the values which are there in the JK flip-flop, you will be using one pin called as a clear pin. So when the clear pin is 1 means whatever the values which are there in the JK flip-flop, that is a memory, it will be cleared or it will be resetted to 0. And we know that the truth table for the JK flip-flop is, so whenever J is equal to 0, K is equal to 0, the output will be follows the input signal what you had. That is nothing but it will be retained as it is, which was there in the earlier stages. So we can say Q will retain its own value and Q bar will retain its own value. When J is equal to 0, K is equal to 1, we call it as a reset condition. So in this reset condition, the Q will be reset to 0 and Q bar will be set to 1. So when J is equal to 0, K is equal to 1, we call it as a reset condition. So therefore your Q will be 0 and Q bar is equal to 1. Now when J is equal to 1 and Q is equal to J is equal to 1 and K is equal to 0, we call it as a set condition. So under this condition your QE will be 1 and your Q bar will be 0. And the very next interesting input signal is the combination is when J is equal to 1 and K is equal to 1, what happens for your Q and Q bar. So in the case of JK flip-flop, when J is equal to 1 and Q is equal to 1, so the output will toggle for every clock pulses. So if there is any change in the clock pulses, the input signal will be toggling manner. So this toggling manner we will be getting in the case of a JK flip-flop which has been implemented through the use of only one SR flip-flop. Okay, so only when we implement a JK flip-flop by using only one SR flip-flop, the output will continuously toggle with respect to the input signal, and that we call it as a race around condition. So in order to avoid that race around conditions, what we can do is we can create a master and slave JK flip-flop. So in the master and slave JK flip-flop, what we can do is when the master is conducting, your slave will be inactive. When the slave is active and your master will be 0. So the feedback mechanism what we are going to use in the implementation of the JK flip-flop, that will not be propagated from master to slave and slave to master in a single clock period. So therefore you will be getting the output will be in a stable at least for the one clock signal. So that condition we call it as a race around condition in the case of implementation of JK flip-flop by the using single SR flip-flop mechanism. So in order to avoid that race around condition, we have come up with a one more type of implementation of a JK flip-flop, that we call it as a master and slave JK flip-flop. Okay, so you can see here this is how the asynchronous state machine we can able to implement for the use for the master and slave JK flip-flop. So this is the asynchronous chart, final state machine charts for the JK flip-flop. So you can see here when J is equal to 0, K is equal to 0 and Q1, Q bar will be retaining the value. When J is equal to 0, K is equal to 1, Q will be 0 and Q bar is equal to 1. When J is equal to 1, K is equal to 0, Q will be 1 and Q bar is equal to 0. When K is equal to 1 and J is equal to 1, the output will toggle between the input signals. Okay, so this is what which is related to your JK flip-flop. So you can see here we can able to implement this JK flip-flop by using the universal gates. Either we can able to implement this JK flip-flop by using an AND gate, or also we can able to implement by using a NOR gate also. The first diagram, it is nothing but the implementation of the JK flip-flop by using an AND gate, and the second diagram whatever we have represented in this slide, it is implementation of a JK flip-flop by using a NOR gate. So you can see there are two combinations are there. One we call it as a master and the second one we call it as a slave. And the output of you can see the clocking signal how we are giving along with the clocking signals, and also the clear signal. So how we are giving. So based upon whenever the clear is equal to 0, the output will be 1. So therefore the values which has been stored over this combinations will be reset to 0 value. If the clear is not enabled means, then depending upon the input sections and depending upon the clocking signal what we are going to apply, so based upon that your output whether it will be reset to values, reset to 0, or it will be set to 1. It will be set to 1. So these are the logical arrangement how we can make out in order to create a JK flip-flop or a resistor.
Completed.
Okay. So the next one is the abstract labels, we call it as, or how we are going to do the testing mechanisms or the verification mechanism we are going to use in the VLSI implementation part. We are going to see it. Okay, so you can see here. So we will be using the first behavioral specifications. So behavioral specifications where you are going to write your VHDL or Verilog program for a particular application. And then for that you are going to check for the syntax errors. So if there is no syntax error means then we are going to do the behavioral simulation, and in the behavioral simulations you are going to write a test benches. So depending upon the test benches what you are going to feed the values, that is the instantiations what you are going to create for the input variables. Based upon that you will be getting the output values. So that we are going to call it as a behavioral specifications. That we are going to call it as a behavioral specification. So once the behavioral specification, that is a syntax error, has been checked properly, then we go for the Rtl specification, that is a register transfer logic specifications. We are going to check it. So in the register transfer logic specifications, so we are going to check the number of LUTs, how much it has been generated, what is the power dissipation of the entire circuit area. We will be checking, and whether the Rtl logic bit has been successfully implemented or not, we will be checking in the Rtl schematic. And also in the Rtl schematic we are going to check for the timing synchronization between one entity to another entity, it is proper or not, we are going to check in the Rtl specifications. So once it has been, and also in the Rtl specifications you are going to study about the peripheral effect which has been produced due to the data transmission over the subsystem, that is a noise analysis has to be done in the Rtl specifications. So after the timing analysis and the noise analysis has been done successfully, the next one we go for the structural specifications. We go for the structural specifications. So means what is the power dissipations over the subsystem, and the power floor planning of the that is a design what we have done, that we are going to analysis. Okay, and the layering architecture we are going to do it in the case of structural specifications. So if everything is correct means then we go for the specific verification. So we are going to implement or we are going to fabricate. So when the fabrication has been done, that is a manufacturing process has been done. So for the manufacturing products we need to do the testing and verification methodologies. So there we are going to create a physical specifications. So the data sheets what we are going to generate, so that data sheets we are going to call it as a specific physical specifications. So for this physical specifications, whatever the product we have designed, whether it is working properly or not, we will be checking based upon a different test parameters. Okay, so these are the testing and verification methods what we are going to use in the case of VHDL or a Verilog design implementation flow diagram. Okay, so